Here's our problem now, our second line integral. We're given this vector field and this space curve that's going through the vector field, and we want to calculate the integral of f dot dr over c. Now again, there's a variety of methods to do this. You want to find the easiest way. So a good place to start is to determine if it's path independent. Now in another video we already determined whether or not this is path independent, but we're going to check again. So the partial of f2 with respect to y, or sorry, with respect to, let's start that over, partial of f2 with respect to x needs to be compared to the partial of f1 with respect to y. The partial of f2 with respect to x is 0. The partial of f1 with respect to y is 0. So this is path independent. That's what PI stands for. So we're going to use a fundamental theorem of line integrals. We can just stop. So the fundamental theorem of line integrals says there exists an f of xy such that the gradient of that f is equal to my vector field values. So in order to use a fundamental theorem, I actually have to find this f, which is called our potential function. So what this means is that when I take the partial derivatives of f with respect to x, it should equal 3x squared. And then when I take the partial derivative of f with respect to y, I should get 4y cubed. So I just have to come up with that function. So if to go from f to the vector field, I have to use derivatives. Then to go from the vector field back to my potential function, I should use integrals. So theoretically speaking, my integral of 3x squared with respect to x, since I have to take the partial of this guy with respect to x to get this 3x squared, so that's why it's x, must equal the integral of 4y cubed with respect to y. In order to get my second component of my vector field, my potential function, I have to take it partial with respect to y. So to go in reverse, I have to take the integral with respect to y. Now this seems lovely and all. This seems very straightforward, but because everything is in terms of x and y, we have a little extra thing to think about. So if I integrate 3x squared with respect to x, I actually get x cubed. But there's also this chance that I could have a function that's in terms of y only. So if I went backwards and I took the partial of this with respect to x, I would get 3x squared, but then this would be 0 because there's only y's in it. But we have to consider that this can be more than just a constant. Same thing over here. Integrate this, I get y to the 4th plus g of x. If I take the partial of this with respect to y, I get 4y cubed. Partial of that with respect to y is 0 because the only variable that's in there is x. So these two things have to be together, so we need to find h of y and g of x based on the fact that those two things have to be equal. So in this case, I looked at the only thing that's a function of y over here is y to the 4th. So h of y is y to the 4th, and vice versa. If the only thing over here in terms of x only is x cubed, that's what g of x has to be. So g of x is equal to x cubed. So in the end, f of xy is equal to x cubed plus y to the 4th. Now, in order to believe that, all you have to do is test the gradient of f and see if it matches our vector field. So let's calculate that real quick. The gradient of f is a partial of f with respect to x. Well, that's going to be 0. That's going to be 3x squared. Then the partial of y, which is the second component here, I need to take the partial of this guy with respect to y. That'll be 0, and that'll be 4y cubed. So 3x squared, 4y cubed. If we look back at the original function, 3x squared, 4y cubed. So we know we have the right potential function. Now, the fundamental theorem of line integrals says this, that if I want to find the line integral of f dot dr over c, all that is my potential function evaluated at the second point, or the point I end up at, minus my potential function evaluated at the original point that I started with. Now, in my problem, the point I end at is -1, 0, and the point I start at is 1, 0. So let's read that. It says top of the unit circle from 1, 0, so that's P, to minus 1, 0, and that's Q. That's exactly what I have down here. So now I just have to evaluate this. This is going to equal f of minus 1, 0, this f, minus f of 1, 0. So if I plug in minus 1 for x and 0 for y, I get minus 1 cubed plus 0 to the 4th, minus, and I got to plug in 1 for x and 0 for y. So 1 cubed plus 0 to the 4th. And let's calculate that number. So I have minus 1, which gives me minus 2. So quickly, let's interpret that minus 2. The negative sign basically says that the parameterized curve is going mostly against the flow of the vector field, mostly against the flow. And the value 2 calculates the work that the vector field does trying to force the curve to follow its flow. Or you can think of it the other way too, the amount of work it takes for that particle that's moving in the shape of the parameterized curve is doing to get through that vector field. You can think of it either way, but nevertheless, that's how it is calculated.